Welcome to day 16 of Calculus. Today we're going to continue our discussion of the derivative function. First, we're going to find the derivative of this nice, wonderful polynomial, negative 4x squared plus 2x. And we're going to use the power rule for this. It's relatively straightforward, where you drop the power to the front, reduce it by 1. So what's going to happen is you're going to end up with f prime. You drop the power to the front, and that negative 4 stays there. The x becomes x to the first because 1 is 1 less than 2. You reduce the power by 1, so it's x to the first plus, and you do the same thing here where it becomes, you drop the 1 because that's the power of x. It doesn't really do anything, but I'm putting it there for completeness, times 2, and then it's x to the 0. It becomes 0 because the power here becomes reduced by 1. You simplify this a little bit and you end up with negative 8x plus 2 because x to the 0 is equal to 1. Anything to the 0 power is 1. So when you have a polynomial, you can use the power rule and pretty quickly find the derivative function. So if we wanted the instantaneous rate of change of this function at any x value, you just plug it into the derivative function. We don't have a rule like the power rule for logs, so we will have to use the difference quotient. As I've tried to emphasize, please make sure you write down the difference quotient to begin with. And now we know that a is going to be equal to 2. There's our a value right there. So a value's there and there. So what do we end up with? We end up with that. So we need to plug in 2 plus h into the function and 2 into the original function. So we've taken the 2 plus h and plugged it in for x, so it's right there. And then we've taken the 2 and plugged it in right there. So you can simplify this a little bit. You could factor out a 2, but the key here is there's nothing you can do to simplify. So you will need to make a table of values where you're going really close to 0. So if 0 is right here, you go a little bit to the left and right of 0. So negative 0.001 and positive 0.001. And then you have, that's your h value. And then this is going to go right there. So you use your calculator, you plug in those these values here and here to find out what the estimates are. So when you use your calculator, please make sure you use the proper number of parentheses to plug in your simplified difference quotient. And then you can use y1 to evaluate this, and here is what you end up with. So these are so close together, you can just pick the first 4 decimals, average it a little bit, but it's going to be negative 0.1737. If you wanted to add in a couple more decimal places, you could, and then average the two. So a great answer to this would be negative 0.1737. You can stop there. 4 decimal places is great. So you could be given a table, though, to find the instantaneous rate of change. So if I asked you for the instantaneous rate of change of this function, now the function isn't given, you're just given the x value and the y value. If you want to find the instantaneous rate of change at x equals 1, you're looking for just the next point to run that slope, the next point. So it's going to be 8 minus 1 over 2 minus 1 is 7 over 1, which is 7. So if you want the instantaneous rate of change at a certain x value, you go to the next one and run the slope there. So now let's find an equation of a tangent line. Tangent line. So again, we know if we're finding a tangent line, we need a point and a slope, because we're going to use y minus y1 is equal to m times x minus x1. This is a great thing to set up whenever you're asked for a tangent line. We're already given the x value of the point. So the x value of the point is pi over 4. If we want the y value, we have to evaluate the function at pi over 4. And yes, you need to remember basic trig. So it's going to be 3 times cosine of pi over 4 plus 2. What is cosine of pi over 4? You need to remember that that is root 2 over 2. It's 2, so this is going to be 3 root 2 over 2 plus 2. If you wanted to add this together to get one fraction, you turn this into 4 over 2. So it's going to be 3 root 2 plus 4 all over 2. You could, if you had your calculator, convert this to decimal, but that is the y coordinate. That is the coordinate that's going to go right there. 3 root 2 plus 4 over 2. It looks pretty nasty, but it's the same process. You find a point, and now we need to find the slope. In order to find the slope, we're going to need to use the difference quotient. We need to use the difference quotient because the power rule only applies to polynomials. So if we use the difference quotient, the first thing I always want you to do is write it down. So there's the difference quotient right there, and we know that our a value is right, gets plugged in those two places. So, and as a side note, your calculator mode should always be in radians unless specified otherwise, so stay in radians. So now we take pi over 4 and we plug it into the original function, and here's what the difference quotient looks like. We already know our f of pi over 4 is right there, and all I did here was I took pi over 4 plus h and plug it into the original function right up here. 3 cosine pi over 4 plus h, and then the plus 2 is there as well. So you need to make a table and find out what this equals. So if you use a table of values plugging in something a little bit to the left of 0, negative 0.001, and something to the right of 0, 0.001, you end up with. So if you use a table, you will end up with this. So that is our slope. That's our m value. So all we're doing now is we're plugging this all together into our original statement right here, point slope form. So we have y minus y1, which was 3 root 2 plus 4 over 2, that's our y1 value, equals the slope, negative 2.1205 times x minus the x value, pi over 4. You stop right there. You do not need to go any further. That would be a great final answer right there. Stop. Okay, let's evaluate a couple more limits here and see what other pitfalls we need to remember you could run into. So in this limit, you're first looking into, can you plug in 2 into this? Well, you can't because the denominator would become 0. And then you look, can you factor anything to cancel out the 2? Well, not really. You can't really do that. So what you really want to do is you want to look at what happens as x is a little bit to the left of 2. What is to the left of 2? Well, that would be 1.9999, right? If x is a little bit to the left of 2, negative 3 times 1.999 plus 4, well, that's about negative 3 times 2 is negative 6. Negative 6 was about negative 2. Well, what's the denominator? Well, 1.99999 minus 2 is going to be a small negative number. Small negative number. Well, a negative 2 divided by a small negative number is going to be positive infinity. Well, let's do the same thing from the right. Let's do the same thing from the right. That would be 2.0001, for example. So if you do that, you end up with negative 3 times 2.0001. Oh, it's squared. Ooh, I missed that. So it's squared. So that just turns it into 4. This turns into 4 right here. Negative 12, so negative 8. It's still going to be positive infinity. So when you square this, you end up with about 4. 4 times negative 3 is about negative 12 plus 4 still is negative 8. The denominator, 2.00001, when you subtract 2 from that, that's a small positive number. Well, 8 divided by a small positive number is going to be negative infinity. What this shows us is that the limit as x approaches 2 from the left of this function, f of x, is infinity, but the limit as x approaches 2 from the right of this function is negative infinity. The left-hand, right-hand limits are different, so therefore we say that this limit right here does not exist. Couldn't factor it, had to test from left and right. We now know that there's a vertical asymptote. What's going on? From the left, it's going up, and from the right, it's going down. Therefore, the limit as x goes to 2 does not exist. Does not exist. This would be the final answer right here. What about this one? Well, we love to factor, so let's see if it's factorable. Limit as x goes to 3, factor it to 5, and you get x minus 3. And the bottom, you get x plus 3 times x minus 3. Something cancels? Absolutely. So you end up with the limit as x goes to 3 of 5 over x plus 3. Well, now, can you plug in 3? You absolutely can. You can plug it in and you end up with 5 over 6. So this limit is indeed 5 over 6. Structurally, we know when you cancel like this, you're creating a hole, and that hole actually is occurring at 3, 5 over 6. You couldn't plug in 3 to the original one, but you can into the simplified form. All you're doing by crossing these out is plugging the hole, which is right there. So the limit is that. If you looked at this function, it'd be traveling along. There'd be a hole, and that hole would be right there. The limit is the same from the left and right. Therefore, we say it is 5/6.